So my name is Siddharth. It's great. Small number of people here. High quality discussions. I mean, it's really awesome. So I'm going to be talking about HTTP2 a bit. It's a very high level primer. It's not going to be very dense, I think, but we're going to talk about the benefits and the fact that it's quite accessible now. And if you are in the business of running your applications on the modern mobile internet, it has many advantages that are now easy to take use of. And specifically, if you're not already maximizing its potential, what are the simple things to do to get to that point? And we'll also quickly show a small piece of working code on an Android emulator, which is basically going to tell you that this actually works in real life. And there are high quality implementations that you can use and in about a couple of minutes or hours, depending on how production ready code you want to write. You'll be basically ready to test the working implementation which works at scale. And again, my name is Siddharth. So I'm the founder of Fastah. I've been doing networking, signal processing, comms, streaming, web standards, and things of that nature across my, almost 14 years or 15 years of work experience now. And so I founded Fastah a few years ago, and we basically make APIs for predicting and sensing network performance from an application perspective, right? And the way we do that is by building maps which look broadly like this. So these are location tagged maps of 4G latencies in multiple countries, and use this to basically make APIs which allow you to.
How do we hide the participant?
It's not getting.
It's not getting projected. It's only on my control.
No.
Oh, okay.
People are not able to see that.
Okay. This is minimized.
Why is this thing? You only know that.
Which things should we press? New share?
No, not new share is fine. Just let's minimize this thing. This done and close this thing. Participant.
There's a floating window.
Yes.
So I'll let you figure this out later. It's not terribly important to the talk, but the overview of HTTP is what I want to start with. So as you may know already, it's the successor to 1.1, which has been the plumbing of the internet for the past 20 years or more. And some of the things it achieves are compression of header fields, multiplexing of requests and responses. I'll go into all of these things in depth in a minute. No head of line blocking, which basically means that the slower requests on your HTTP channel are not going to delay the requests which come after it. And again, I'll delve into the subtlety of why that matters a lot on a high latency mobile channel in the next few slides. It does header compression, which I mentioned already, which are headers are very expensive because a lot of them need to be transmitted again and again given how the internet has evolved. And the servers expect to see them again and again on each GET request or PUT request or POST request. So there is a lot of repetition on the internet, and this protocol helps with some of those things too. So I'll give you a quick big picture overview. What was that? So this is a big picture overview again, diagrammatic one though. So you are still running on top of TLS. Nobody in the wild has implemented an HTTP built not on TLS. So everybody is implementing HTTP2 on TLS on a secure channel. Technically, the specs does not require you to have TLS as the layer below, but real world people have implemented it in a secure manner by default. So that comes for free in practical implementations that you wish to deploy in the wild. In terms of how the HTTP semantics have moved, or rather been incrementally enhanced or encapsulated, you may use the term you wish, but the way it has worked is that frames have become the new sort of unit for logical expression within that protocol. And things which you used to say get or post, which is the example in the gray box on the top, are encapsulated within a header frame and a data frame, right? So the data frame is your payload for the example, that JSON document message hello that you see. is the payload of your request in the current HTTP 1.1 era, and that has been transposed to the data frame in the new world, and the header frame is what you see as HTTP headers in current 1.1 standards. So I think the fun stuff starts here when you start zooming out a little more and noticing that there are things called stream, and streams are supposed to carry multiple frames back and forth. And this also implies the figure below, specifically the lower half, is that streams can be effectively multiplexed logically, right? So they can be outstanding frames going from the server, which have not yet been received by the client, and they can be frames going up from the client up to the server that have not been received by the other party. And those don't need to wait for each other. So there is design. One of the design goals of HTTP 2 was to basically maximize the bidirectional throughput of a channel, realizing that requests and responses are the basic grammar, and people or applications don't just request one thing at a time. They can be requesting dozens of resources at a time. So, for example, if you make an application for, say, Flipkart or an Amazon shopping cart, you will be requesting dozens of images at the same time. When you load a screen, you may be loading some icon images, for example, for your control buttons. You may be loading pricing information and other product details in the background. And those may be a dozen API calls which you are shooting off to the server, and those are just required to populate one screen, right? Or to update the screen that you have rendered from your application on the client side itself. So realizing that both application use cases as well as web browsing use cases, and as you know, web browsing also depends, and modern apps depend on XHR and multiple background API calls, web API calls all the time. So how do you maximize the concurrency in terms of network usage of those back and forth was rather the explicit goal of HTTP 2, and that is what you see implemented in the standards. So there is a very high level of concurrent network operation going on when you map requests and responses to the HTTP protocol layer. So this is basically the same thing. You can have multiple streams with their own headers and data traversing the network at the same time. And you can have upstream and downstream communication happening in concurrently, even at the request and response level, right? So what this means is that, again, like I said, if you have a screen which has images of your piece of clothing, for example, that you're selling on an Amazon app, the images for that product are being loaded at the same time the request for, say, a button artwork or a theme file or other assets are being loaded. So the same server is being contacted for all of those requests. There is one TCP connection open with that server. You don't need to have domain sharding, which was used widely in web performance. I don't know how many of you have worked on web performance, but it was very common to have static images on one server, JS, JavaScript, and CSS files on one server, and API and other WordPress servers on another server. So some of those things still work, but just for the sake of maximizing HTTP performance, you don't need to do domain sharding anymore. Because there is implicit parallelization and concurrent network usage within HTTP2. And just because your image catalog is taking too long to load does not mean that smaller static images which are quickly returnable by the server are not going to come down the pipe quickly. And on your client side, your application will know that those have finished, the HTTP gets for those, and it will quickly, hopefully, load them in memory and render them to the scene. So there are basically non-blocking HTTP operations when you do them at scale, talking to the same server. This was not possible before. So request prioritization is also something new, and this comes from the web performance area primarily, because as you might know that on a web page, some classes of CSS content may prevent the rendering of the page because the browser does not have enough style information, font information, or some other genre of things to do a first pass, parsing and painting of the document to the screen. Or in some cases JavaScript too. And There have been guidelines on how to optimize it, how to minimize the dependencies which prevent a browser from painting the document to the screen, just when the HTML has become available. But request prioritization is a way to give the browser or an HTTP library the ability to specify the priority of a resource that it's requesting, so that the server starts sending them first, and if necessary, tells the backend server that, hey, this query, for example, needs to be returned the fastest, so run that at a higher priority, or do other resource allocation hints in the backend. Right? So user agents, which means either browsers or your library on your app, can basically tell the server what resource load is more important in order to minimize whatever metric you're trying to optimize, hopefully time to view for your shopping cart or time to view for your website. Server push is something which is also very interesting. Server push is when the client has not requested something, but the server decides that this is something important for the page to be loaded, and I'm going to send it anyways, right? So what it effectively does is it primes your HTTP cache on the phone or on your app on your browser. These work transparently to the caching system. So any HTTP cache that you have on your user agent or on your client side are going to be magically populated just because the server said, hey, user agent, take this file, you'll need it later. So without the user, without the browser or your app explicitly requesting a JavaScript file, for example, that JavaScript file can be speculatively loaded into your local cache. So you don't need to go get it again and experience latency with any application. So this is the example of the push, and so for example, in the lower half of the screen you see stream 1, which is say page.html, which is the top level HTML page from a website. So that of course the client explicitly requested, but then before the client could get the HTML, parse it, go through the JavaScript tags and see what JavaScript files were needed and go fetch them again, the server said that, dude, you need this already and I know this, so I'll just send it to you right off the bat in the response, together with the response of page.html. So the client doesn't need to parse the whole document, it doesn't need to prioritize the requests that it needs to load, shoot them off to the network and then wait for it to come back in order to parse. So multiple round trips have been eliminated, and this together on a grander scale, when you club 100 requests that a typical web page, modern web page actually creates, this substantially reduces the round trip time that your browser needs on a mobile network or any high latency network to actually have a viewable or a browsable page rendered on the phone. So this is a very classic web performance heuristics and browser heuristics making their way into a Go protocol. They're actually going down the stack, right? They're being pushed from legacy HTML that the world needs to interoperate with other HTML pages of the world, and things need to move fast, and those things have been packed basically downwards into the stack. So this is a very fascinating evolution that I've been part of for the past many years because I worked on WebKit at Nokia. So this was all being discussed then, and this has all become basically out of the box available now on both the server side and the client side. So it's really fascinating how it has moved. Making multiplexing work, again, most modern web servers are supporting this out of the box. Load balancers, I think all cloud providers also supported. And they may be doing the termination of the SSL connection at the load balancer, but I believe they might be doing that even for regular HTTPS 1.1. So that you'll have to be slightly aware of, but that's not a big deal. So the HTTP client library landscape has evolved a lot in the past year. I think everything from PHP on the server side to Java, Android on the client side to certainly iOS, they all have high quality working in the real HTTP libraries. We also have an app that we shipped with HTTP2, and for our use case, ours is a slightly easy use case for HTTP2. It's definitely not as complicated as an Amazon app or a shopping cart or a complicated shopping cart. But for our limited purposes, it works quite well. I'll show you a quick demo, but Google Cloud is what we use. And Google Cloud servers which serve HTTP content from a bucket, from their equivalent of an S3 bucket, which is called, I think, GCP. What is it called again? Google Cloud Storage. So a Google Cloud Storage bucket is equivalent to an Amazon S3 bucket. If you turn on HTTP serving on it, I think out of the box or with just a checkbox, it automatically supports HTTP2. So you don't have to run your own server, you don't have to configure it. Most cloud servers are working out of the box with this now, which is awesome. OK HTTP3 is something that I was slightly familiar with, so I want to talk about it.
This can be used for assets, for example, JavaScript file,
You don't
assassin tag in the script, the assassin key in the script tag, things like this. Or does it also work with making
It will. Absolutely. So I have I have looked at the Go implementation of the HTTP2 server to an extent, and again the way all of the APIs on the server side implemented, they expose all the hooks, no matter whether you have a browser user agent or you have an app which is making API requests. So they all work identically. All you need to do is, for example, if you are showing a shopping cart, right, on an app, are you thinking of an app, not a browser? Is that the use case you're thinking of?
Then also we have some resources. Is this work only for the direct things?
No, it can work for indirect things. Right. So from in a browser, for example, we make a call to myserver.com/ grab my stuff. Okay, grab my stuff is your URL endpoint, or rather the page, right? So on your handler on the server, you have implemented an HTTP2 handler for grab my stuff, right? So when you see a request for grab my stuff, you say, okay, HTTP2 okay, finish that response, and then trigger the callbacks for two pushes, server-side pushes, or say 5. Let's assume you want to send 5 documents into the browser's cache when grab my stuff happens, right? That's what you want, right? So then from the callback of grab my stuff on the server side, when you're writing the response and closing the HTTP 200 OK, you can trigger the callback or the event which tells the server to go write those 5 files down to the client using that connection, right? So you can intercept the request. The client still has to initiate because you need to have an active connection. But the moment you're ready to finish writing your OK response to grab my stuff, you tell the server, I need to send 5 more things down those 5. And those will automatically be serialized to that connection, and that's it. So you don't need to write anything for grab my stuff. It can be a 0-length response with just a 200 OK response. No body, only response. But once that is written logically by the HTTP2 server, it can immediately start serializing the other 5 files, just like stream 2, stream 3, stream 4, and stream 5 in this example. So yes, you can do that. You need to write your own server, obviously, is what I'm implying here. You can't say caddy server, go fetch, go do this. I haven't figured it out. Rather, I wouldn't be surprised if that was not possible with an out-of-the-box server. You'll have to, of course, write your own implementation. But Go, for example, has very good HTTP2 server handlers out of the box. And I think it should be quite straightforward if you're doing your own API backend to implement it. Yeah? So yeah, I think the APIs are flexible on the server side. So if you're using the right library and the right framework, it should not be hard to basically do what you're doing. The protocol does not close your opportunities at all. And HTTP2 has no philosophical problem with what you're trying to do. It is designed to support that use case. HTTP2, OK HTTP3 is quite nicely used in Android apps. This is an example code. I'll show you a quick demo. I think the important thing I want to show is that it looks nothing substantially different than any other networking library. So you have a builder pattern that people who do Android are intimately familiar with. You don't even have to enable HTTP2 by default. It out of the box works with HTTP2. Like any other good HTTP library, you can configure cache control policies, max tail, and other things. Here, for example, I'm saying that if for this request you are asked to force reload, you do a no cache load of the resource. So this has nothing to do with HTTP2 or with OK-HTTP3, but I'm just pointing out that the OK-HTTP3 API does reasonable things like HTTP2 caching, whether or not the transport is HTTP or not, right? So all the well-known performance-friendly semantics of HTTP 1.1 and the old world, they continue to work in this new era too. So that's the top of the code. And once you have a request, again, this is a builder pattern. You do a call function, which actually does the actual request. As far as I remember, this is the blocking way to call it. There are also the non-blocking ways of doing it, and install an event handler to catch an error or a success. And in the lower half, I'm showing you that I basically generated this new request for GET for this URL from storage.googleapis.com, which is Google Cloud's storage bucket. Like I said a moment ago, you can dump static files on it or a static website on it, and it's going to automatically serve HTTP2 right off the bat for you and detect basically if the client says or advertises that it supports an upgrade to HTTP2. So in the response, I'll show you here. The second log message is okay, HTTP response is successful. Protocol is H2, code is 200, and message is blah, and URL is this. So protocol is H2 is what you need to look out for. So protocol H2 means it's talking HTTP2 to that server. And once it loads this, it actually shows these maps because that's what I'm loading here. I'm loading a gzipped for tile layer, which is basically being used to draw these colors on top of a map. So just for fun's sake, I'll actually clear the cache and to redo the request, and we'll see if the log message comes back. And then you can know that it's actually working. So I'll go to the Android way to clear the local cache. I'm actually clearing the HTTP cache, because the HTTP cache is parked in the apps cache area. So now if I relaunch this puppy, it should let's see, if I kill this and launch it again, maybe it will work. Come on. Quickly. There you go. Yeah, there you go. See, so the log messages came back, in case you noticed, and they came back with protocol equals HTTP2, port 200, and this, right? And then these tiles got painted again. So this is actually working through my Airtel hotspot here. So it is working on a regular Airtel network perfectly fine. We ship this in production in about 5 countries in APAC, and it works quite nicely in all of those. We haven't seen any significant problems with this. On all mobile operators, of course, our app is used only on mobile networks vast majority of the time. So this is pretty good. The other thing I want to show you is that this is great, but what more do I have in terms of debuggability? Because when you want to ship a complex app and you have 50 requests going out at the same time, just like your Chrome DevTools shows you requests and waterfalls and those ways of inspecting requests and responses. So this OK-HTTP has an architecture called a plugin architecture, which is called interceptors. So I would highly suggest that you look at So use Chrome browser's web inspector to inspect your apps HTTP request responses. I'm talking about apps here, actually, not the browser itself. And I'll show you in a moment. And there's a plugin called a Stetho plugin, which Facebook has open sourced. It's a plugin architecture that you can use in native apps on Android and I think on iOS too. And you can connect your app to your browser through your debug cable or USB cable, and then you can inspect the DOM, quote unquote, or the application's memory space, and specifically the view objects in the UI hierarchy, the network request objects, basically any things in the Chrome DevTools UI. So the Chrome DevTools UI has an API which is extensible. So not only can you deconstruct web pages in Chrome DevTools, but you can also write a custom data into a Chrome DevTools UI and make it show requests and responses there. So the way that works is HTTP3 running on your Android phone, which I showed you in the emulator, has this concept of interceptors, which, as you can see in this figure, they plug into two places. One is the network interceptor, which is going out from the core networking layer, out to the network. And the other thing is coming back from the cache back to your application. So you can process data, application-specific logic. You can package that in the application interceptors. For example, if you have some proprietary, byte stream protocol that you're, encapsulating data with, and you want to, decompress it, you can do that in an application interceptor. If you want to do some other magic in a network interceptor, like take the copy of the data and give it to Chrome DevTools, then you can write an interceptor that does that. And the OKHTTP guys have done exactly that. They have written a plugin, the interceptor that takes the data coming down the wire and it dumps it into Facebook Stetho. Facebook Stetho knows how to work with Chrome. So basically you now have a chain of plugins which take your network response request data and then dump it into Chrome DevTools all from your phone, right? Your phone is connected to a USB to your laptop, and then the whole apps networking library gets exposed to your browser on the Mac or your Windows machine or whatever desktop you're using for debugging. So the way this works is that what was I going to show? So I was going to show this Chrome. So this is Chrome on my Mac, right? So this is the Chrome on my laptop. And in the Chrome inspect devices, this is the URL you can use to scan the devices which are connected to your Mac, and it is able to inspect debug sessions from these devices. So you can basically hit reload and it should show you that my Pixel is connected, which is this modem that I have connected right now. And of course the Android emulator, which is what I've been showing you with those colored tiles, is connected to this Mac also, because it's running on a virtual machine in that. So this is the app, so I can say inspect, and this shows me a very familiar Chrome DevTools UI that you can use to easily inspect requests and responses. So the elements, which is basically the UI of the app that I'm running and the main UI activity and the UI object view. I don't need to look at all of this right now, but if I wanted to, I could do. So I can see various UI stuff on the phone, but the network tab is what I'm primarily concerned with here. And I haven't been able to make this work, but the idea is that once you do the same thing that I did, which is clearing the cache and reloading this HTTP document, so it actually goes out to the network and fetches it from the Google Cloud server, I should be able to see the Chrome DevTools UI show that the network request came in and inspect all the headers quite nicely without needing to log every header on the console or the debug console or other logging tools which you use on Android or iOS. So I cleared the cache, and let's see if this works. Usually, okay, this was so fast. So, so I don't know why it's not working here. Maybe I initialized something wrong. But the idea is that this is working correctly, and this is, I think, the proof of the pudding. This is the log from my Android code being printed on my development environment's log window. So I think this is the proof of the pudding of it running on this. But once you set it up correctly, that Chrome DevTools should be able to show if you're doing 100 requests for each screen or each app start, you should be able to see any or all of those in Chrome DevTools. So any serious application which has multiple servers being talked to should be able to do it more elegantly and with higher developer productivity. So I think that's all I wanted to show you. The code for changing this, so the libraries are quite simple. And like I pointed out, there is this interceptor architecture for adding your own custom behaviors, right? So this is how the HTTP client has been configured, which means the singleton object, which is shared by the whole application. There was a cache configured in the third line. There's a network interceptor called the Stetho interceptor. Stetho, again, as I said, is that Facebook library. So the OKHTTP guys wrote an interceptor, like I showed in the architecture diagram, to expose data coming in down the wire into that framework, so that Chrome DevTools could start discovering that. And the third thing I've shown here is my own thing. So add network interceptor is something that is sort of proprietary behavior of our app. And what I am showing here is that we have made a policy here which is custom. So for example, what I'm doing here is that I'm being more aggressive. Okay, so our app is supposed to work even when you're offline a lot. So what we're doing here is we're making the caching policy work better for us. So if we have poor connection, we are going to use the cache data at all costs, rather than go try on the network and go fetch a 10 megabyte file. So we are sort of breaking the protocol HTTP caching standards by making it work harder for our use case. So any custom use case where you have the needs to power adapt the system to work for you, you can write an interceptor which has only say 3 lines of code here, right? So this is a lambda function or an inline function that I wrote. You can see this chain this is the new interceptor with a method called intercept. So that's the implementation that I wrote. And this gives you the chain object. You take the request out of the chain object, and then you do only if cached max tail, and you bump up the max tail a lot. So we detect if HTTP cache is strongly preferred, then you basically err on the side of using the cache, even if it's stale, the data on the cache. So it says like custom networking policies you can write with interceptors, and that's what I'm showing here. I'm showing one use of a Stetho interceptor, which is doing those things I demoed to you, and I'm showing you our app's own behavioral modification that we did with 3 lines of code using OKHTTP. So whether it's HTTP2 related or not, you can still do a lot of things with this amount of pluggability and extensibility in the architecture. And for example, this strongly preferred is just that, if your connectivity service is weak or your measurements of the network are weak, then you do certain behaviors, like using the cache more aggressively, for example. So anything you can do, any sort of custom logic for inspection as well as behavior modification, you can do with this architecture quite elegantly without breaking a sweat. So yeah, I think that's it. So I think I've explained how HTTP out-of-order requests work, the fact that it's widely deployed, and an example of a library. By the way, OKHTTP is pure Java. So in case, I picked this purely because I'm comfortable with it and I use it on a phone. But if you use Java on a desktop, you can easily program with this both on the command line and on the IDE. It's a pure Java implementation, so it works quite beautifully in either case. So if you want to prototype things with it in your work, it's quite easy to try. And you don't have to have a phone at all. It works on a laptop. It's actually quite elegantly. So I think that's it. Any questions? Yes, please.
By any chance, is it possible, or do you have any numbers to code vis-a-vis the regular HTTP number versus HTTP2? How much of it provides you for application? Latency-wise, or latency-wise?
Yeah, so I don't actually, but I can find it out. And there is extensive documentation on HTTP mailing lists and on public docs that Google and others have published about use cases. So there are so many use cases and so many cases around round-trip minimization that as a person who's been doing HTTP networking and caches for a long time, I think for the most egregious cases, you would see a 10-time improvement in round-trip times or page loading times. Because the thing with round-trip time and the people keep obsessing about RTTs and networking community is obviously because people thought that when DSL was going to fiber, latency would no longer be a problem. But then we had 3G becoming the default, and then we had 4G becoming the default. And now we have all of India watching internet on 4G or Pornhub on 4G. So now we have a new set of problems, right? But so there is very always by design or by nature, very high variability in latency. And if you can minimize round trips at all costs, whether at the application layer, the transport layer, or there below, the performance goes up non-linearly, right? It's like 1 to the power 2 or 3 or 4. It's an exponential or a more than linear improvement in performance. Because the semantics of TCP, like is you need to send a ACK back, and then you can send the next.
So TCP is very tight.
Right. So you were using the word throughput yourself, right? So
all the latencies.
Yeah. So when you reduce the latency, the throughput goes more than linearly up, right? For a proportionate, 0.5 multiplier of latency, the throughput goes up vastly more than 0.5x. So I think it really depends which use case are you hitting, or what bottleneck are you hitting in your communication layer. Or in the case of this API multiplexing, right? Like you're trying to load 5 images of a chudidar kurta that you're buying on Amazon.in on the fashion store, and you're trying to load the images for the buttons, the help chat, the blah 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 at the same time. So that obviously depends on your application and whether your API backend is loaded, right? Because APIs are not born equal, right? One of them is querying a database, is doing a join on query, and it will take 5 seconds to come back to you. So the other guys don't need to wait. Just because the 5-second query got out earlier, and you can't control its ordering in a Java layer or an application layer easily, you shouldn't have to wait. So, how do you quantify that? That's a very application-specific quantification. So it's just, for a non-trivial API application, the upsides of this are staggering, is all I'll say.
Just one more thing one of the things that we encountered when we thought about HTTP was that the concept of streams is great to have, but it uses now you have a single TCP connection having multiple streams.
Yep.
Earlier you used to have multiple connections, TCP connections.
Sure.
Now the impact of congestion control. Earlier you were having 5 connections and it was downloaded data in parallel with 5 connections. Versus a single connection which has a single congestion control. So, did you guys had any observations or any sort of because that would negatively impact HTTP?
So why is that a problem? I don't understand.
It positively impacted.
It's a positive impact. It's a feature, not a bug.
So let's say, for example, there are 2 applications. One application is deploying HTTP1. Another is deploying HTTP2. Both of them have 5 streams virtually. The HTTP1 application is attempting 5 connections. It is getting a fair share of the 2.
Okay. So are you talking about network fairness now?
Yes.
Okay. So you're not talking about individual applications throughput. You're talking about network fairness at a society level, like internet governance.
So let's say, for example, the example that I gave you, 2 applications. One is using HTTP1 and another is using HTTP. Both require 5 streams. HTTP1 does it using 5 connections, another does it using single connection. So is application 1 going to get a fair share of?
Not really.
Not really.
That's what I want to understand.
The reason is that most of the time you start different connections, you are not constrained by bandwidth. So even 1 connection or 2 connections, you can actually push through a lot more data because there is no head of line blocking. Even if you have 5 connections, a lot of them because of HOL will be idle some part of the time. Right? Like the example that he quoted, saying that you are waiting for the database to come back. But by the time database is going to come back in the same connection, I can push in all the resources, which is what he showed in the promise, the web push kind of model, right? So I can keep it ready. So earlier, if you see, so I used to work for Harvard, you know that, right? So the way we used to work is to optimize is you have these caches. You get a web page from the cache, and you have an origin server. Right? So now the browser has downloaded a web page. It's going to make those requests to the cache. Now the cache knows it because it's passed the page. So Atma and other cities, what they used to do, they should get the content at the edge. So by the time you request it, that round trip time actually reduces it, which is kind of segues back into this point saying that you reduce the round trip time. Because at the end of the day, it's physics, right? I mean, there is distance to be covered, and you're bound by the law of physics. So that is why all network optimization obsesses about RTTs. So coming back to your question, yes, I mean you can theoretically, and again there is context is important, but it is not necessary that just because you have 5 connections in HTTP 1.0, you will utilize the bandwidth better as compared to HTTP. Because it's like you have one pipe, inside that pipe you have multiple pipes. So it's like 5 connections in one. So that is the concept of the stream.
Basically, the sliding windows are 5. So all of those 5 are independently tuned, and they are not unable to individually reach the maximum of the channel. So here there is
you have more data also, right?
Yeah.
Both the endpoints have more data, and you're pushing in more data in terms of metadata also, and you're pushing in more data. So you have more data about the state of the connection.
Correct.
Whereas
you're sampling the data more finely, you're sampling the channel more finely. Is what you're saying. Hence your statistical model that you alluded to, that the transport layers know much better than either the L3 layer or the other layers. Those models are precisely better because of this. Hence the TCP internal variables are able to achieve a better channel utilization by moving their window sizes and other buffers that they adapt to much better. And hence the metrics that they come up with about variance, jitter, those by extension are also better. Because now 5 HTTP GET PUT requests are consistently measure both the uplink and downlink channel from the same IP pair to the same IP pair of the same 2-tuple IP basically. Right? So it's a sampling problem. Coming to your talk's point that TCP layer knows its stats the best. Right? So you're basically sampling the problem more finely now than you would do in 5 different connections, because each of those would have their own TCP stats structure in the memory of the kernel.
So from the TCP layer point of view, you have 6 connections. One application is having just 1 connection, other is having 5 connections. Let's assume my DC connection is 1 connections. Those 6 connections are those, and with data sharing, the input sharing, will be across 6 connections.
No, that's not how it works. The one socket connection can max out at 1 Mbps channel.
Yeah, it can.
So there is no God-given reason for that 6 channels can use 1 Mbps better than one socket.
So let's assume that we are fetching more data from both the application. We are trying to fetch. I mean, it's going to be maxed out. Whatever my connections are, the connection is going to be maxed out. What I'm trying to understand is the application one is because TCP will share equally across these 6 connections.
No. TCP, why would TCP share across these 6 connections is the presumption that I'm not understanding. Why? There is no such requirement in the TCP stack that there are 100 connections on the TCP layer of an operating system. Those are going to get the same amount of bandwidth.
Yeah, because it depends on the tuple, right? Like for example, if connecting to a local cache as compared to connecting to a VPN layer somewhere, the network latency for the VPN is going to be longer and actually decide on the Windows side. So another comparison, just to contrast that, would be like you're downloading a large file in one connection as compared to you're downloading lots of small files in the other connection. Right? And because you have a large file in one connection, because there's a lot of data coming through, you will converge at what is the max speed much faster, which is what the sampling problem was. That is another way of kind of looking at it. Except that it's not one large file, but a lot of small files which abstracted at the application layer.
Yeah, so there's no reason for you to believe or for anybody to think that if there's 6 sockets end-to-end TCP connections given to a kernel, there is no channel gets divided into 6 slices assumption there at all.
It's not
from
like
a transport layer perspective.
It's not like round robin. I won't round robin.
There is no
very connection specific. Connection and actually on the network partner specific.
and hence buffering occurs and sliding occurs by derivation. Right? So the fundamental thing, like I said, is the other party acknowledging you? Is it fast enough?
Yeah.
Over the next 30 seconds, 1 minute, if the transmissions continue up and down, what are the averages and the jitters and other stats like you said? And by extension, should we improve the buffer size and send larger blobs of data up and then wait for all the acknowledgements at one? Or should we keep sending 1, 2, or 10, or 100, or 1,000 packets and then wait for the bulk acknowledgement back? Right? So that is the only thing which the effective throughput of a two tuple depends on. So whether the kernel happens to be handling 10 or 1 socket is limited to that performance stat. I mean your Ethernet card may not have capacity, but usually Ethernet cards are not assumed to be the performance bottleneck. They're assuming that the connection between your server and the app is so far away or so lossy, either of those things, that those is the determining factor for your TCP connections, effective throughput.
So, Siddharth, I was just looking at some statistics. It looks like the adoption rate for HTTP2 is about 33%. So, you can expect that to go up.
Well, absolutely. It's a miracle that it's 33 already. It's such a new implementation in the wild.
Yeah, but it's like 3-4 years since it was standardized.
Yeah, so the speedy thing started as a hack, and of course Google's market weight and monopoly in the browser era helps. That they can do the server hacks on the Google websites and then the Chrome hacks. So I think that really accelerated. Actually, if you say a lot of smaller parties cooperating is more frictional than Google trying to do things unilaterally and then saying, okay, let's standardize this. So I think that there have been some hacks that they've done for the better. But Squiddy did a lot of wild trials through Google's infrastructure, and that accelerated the standardization process for that, and hence the deployments in Caddy and other Go servers and other modern infrastructure, internets of course.
Right, in most cases, actually, from implementations, it's just like a switch. You enable HTTP. The application doesn't care. Right? It's just, as far as doing it, just like writing stuff. So, if you're an application developer, you wouldn't care less. It's just that you get data faster or more through. Also, one thing that helped is Google pushed it, but also having this they were very fast. So typically, many of these guys are slow, but I think because of they knew that this would make a huge difference to their customers, there was a race between them saying that we will do it, and that's why it got turned on by default for a lot. It's been like a year and a half, I think, when the standard actually came out, but the implementations were there in the wild even before it became a standard. Which is kind of unusual, I think.
That's because there was Chrome already talking on half the world's browsers. So both mobile browsers.
So there was pressure, because there was this pressure and competition between different CDN vendors, and also the application client side also, the customers also were heavily pushing, because as you said, like domain sharding, loading case before, there are multiple tools also. So all of them they had maxed out. So this kind of came at the right moment also. Got adopted.
I think it's going to go up, those numbers. It's just, I think it's from 30% is a very big number.
Yeah, if you see, just to your context to see like the IPv6 is pretty bad comparison, and it's also at a different level because it's same physical equipment compared to application which are. But if you even look at DNS, like for example, which can to some extent can be comparable, it's an application layer protocol. You see the adoption of that versus this. I think HTTP2 is quite fast. It's actually surprising that they are already talking about HTTP3 because
Sure. And a lot of the transport TLS 1.2 and 1.3 things are starting to getting woven into these and designed more together. So I think the whole encryption story and the HTTP2 story and 3 story are generally working somewhat in tandem. So I think the whole Snowden thing also kicked the TLS battles up a gear substantially. So the TLS 1.2 and higher evolution really became much more accelerated, and that also has helped the HTTP2 adoption. And most of the web servers handle those seamlessly these days.
That was the other big push.
Forward sequencing, modern ciphers, and all of those nice things.
In the HTTP spec,
Does not.
TLS is not
Correct.
mandatory, but it grows.
All
It's kind of a de facto standard because now, I mean, again, like TLS 1.3, there was a huge fight, but they said all the browsers who had large markets like Mozilla, Chrome, Safari said we are going to implement it by default. So now it's like if you're using a browser, you're using HTTPS. And that kind of became the default. And HTTP2, a lot of these things were actually built in HTTP2 because so people wanted faster stuff. People also wanted more secure stuff. So one customer was asking for it, and then the game cannot play because multiple people are completing it, got adopted really fast. And yeah, Snowden, as you rightly said, like this conversation was there in ITF for a long period of time, and Snowden just came and then it just became like an insane thing. People became like super
he's a public key cryptography, and basically TLS has never been easier usability. This whole let's encrypt thing is amazing.
So
it's only a year old. It's only started after Snowden, I believe.
Yeah, and so not just the protocol. You see the vendor support, what customers are asking for, the tooling, the open source tooling, like let's encrypt. Or even if you see adjacent protocols like ACME, for example, certificate management. All of these kind of came together at the same time, and then basically if you wanted all of these, and there were different dependencies, you kind of adopted this new kind of stack. And from a deployment point of view also, like if you look at Light HTTP or Apache, it was just an option that you could turn on. So it was actually much easier than like IPv6 or what MPTCP would go through. So there were so many different forces like security and Snowden. Then there was this maxing out of the bandwidth, and also the tooling around this. All of it came together very nicely. So I mean, all of these forces actually pushed it quite. Because if you see like the DNS second, all the tooling and other thing is not that great still, and data because of that it kind of.
Absolutely. Cool.
It's about the streams versus connections. On mobile devices, you would actually expect some amount of packets. So because all of your streams are using a single TCP connection, you lose a packet which is related to one stream. You will end up again having a head of line blocking for the other streams because TCP has to deliver. So if you actually have a mobile network which is very significant process, wouldn't it have a similar performance?
Yeah, one could. Yeah, I think some of it. So one would presume that if there's one packet loss, presumably it belongs to one data frame, and that data frame belongs to one request response pair. So one would think that that request response pair would get delayed.
But still, it cannot be pushed to the application because TCP will not
Right. But the other request response pairs, if the TCP layer is able to acknowledge those ingredient packets, should go ahead, right?
Yeah, it's still sitting there.
Yeah, I think it depends on, yeah. So I think the question is really about then the TCP window, how it's working for the acknowledgements, and is it going to retransmit the whole window, and how many frames happen to sit in that window?
Still, you'll end up having head of line blocking at the TCP.
Yeah, potentially. I think they, yeah. So I mean, the TCP has to wait for ACKs, even though that has been optimized quite a bit in the past 10 years.
Actually, ACK is fine. Now you have, say, you have three data frames which you've got across three.
No. So why are you saying ACK will work? So your question is about TCP packet loss, like layer 2 packet loss or layer 3 packet loss.
So suppose there are 5 different streams, right? The same connection. You lost a frame in which maybe 3 data frames got lost.
Packet. You lost the packet.
You lost a packet in 3 different frames across the different streams. But the other packets will start queuing in, and you can still read those packets.
Then they buffer at the TCP level, right?
They basically sequence.
In order. Can't read something.
Quick solve this issue. Quick.
They might be that. So I think the question really is like for a 1000 by 20 frame for an Ethernet packet or a transport layer packet, how many frames are they trying to packet into it? Or even if it's one frame, assuming for the sake of discussion, how much does that ingredients of a single frame getting lost impact the net throughputs of your HTTP gets inputs, basically? Yeah. So I think there is some causal effect there. Yes.
HTTP1 might have advantage here because it is.
That said, we'll have to see what are the modern TCP buffering algorithms we use, because selective acknowledgement, there have been a lot of improvements shuffling into the Linux kernels over the past 10 years.
I think it's the problem is because of the protocol. TCP says you can only
Yeah, but the packet loss problem has also been improved.
select
Past 10 years at the
you mean
TCP
through
kernel.
better
Through better acknowledgement handling.
Not just
Yeah,
acknowledgement handling is important.
including loss, packet loss issues.
Any of the changes, any of the changes to the acknowledgement mechanism of TCP hasn't changed. When it changes, what you acknowledge, and the buffering mechanism hasn't changed with that connection.
No, you're right. I mean, that part, they are right. Like, you will always read it through. So until that rule is filled, you can't
But show the clarification.
And then, like you said, the UDP use cases start kicking in. It's out of order delivery and how to maximize throughput for out when out of order is open.
How does it
So they can, even if it's out of order, you just use it.
You were saying something?
I think with this kind of implementing TCP, I hope there is this famous second system syndrome, right? I hope that doesn't happen with Google, and let's see it happening. People who could not get their stuff into TCP because TCP is also right now, they want everything if they can. Yeah, then you have problems. We were just talking about tunneling, for example, right? So this famous example, like why security is such a high problem, is because some amount of layer variance. So you had virtual circuits, which was like end to end, and then you had IP, which was like disconnected and discrete packets, and then TCP, which was like end to end. And then you had HTTP, which was again disconnected discrete packets. On top of that, now you have HTTP2, which kind of implement some part of TCP, which is why these questions are coming. So yeah, I think that
You can't re-engineer the whole world at the same time. Right?
tunneling after tunneling after tunneling. And even at the network layers also, as I understand more, I think the same thing is happening because something is out there except the market, you can't change that. So you kind of build your stuff on top of that. So it's kind of getting layered and some things are becoming better, but some things are also.
But I think I can tell you this from my personal experience. Like 2005, 2004, I was in the US helping carriers do RTSP streaming on the network. Right? RTSP uses TCP and UDP. Their firewalls were really uncooperative, and all the network engineers said there's no way we are going to apply these random Cisco patches just so that you can get your videos from the world. So I think given how fast the consumer internet landscape moves now, both browsers, web tech, and apps and Android and cheap LTE phones, I think the willingness of hardware makers in intermediate areas to upgrade their infra and apply software and make their Cisco OS be the latest and greatest. I think that has become vastly better than it used to be. I think it was positively killing us back then to be running any video streaming services back then on networks. So things have moved on to HTTP and everybody has given up on UDP at the transport and the application level. That has also happened, unfortunately. But I think some of the vitality of the whole sector has actually improved out there. It's still much, you have 2 or 3 years and people are upgrading their routers and upgrading their firmware, not like 5 or 10 years, which used to be the case 10 years ago. So I think there's hope that things will on the aggregate be less choked at hardware abstractions for deployed gear.
You said you had like 4 different protocols. At that time you had your player, you had Microsoft had some Windows Media Server, or something like that.
Flash has its own Flash.
Yeah, Adobe Flash. And all of them were competing, so all vendors were like implementing 4 because some large vendor would say, okay, I bought into the Microsoft ecosystem. And everybody had their own product, so it was a nightmare to do. And then YouTube came along and we'll do their own HTTP and change the game.
Yes.
Right, so actually YouTube would have an unfair advantage because everybody else was trying to figure out this and we don't get that. I'll send packets over HTTP. I'll use not TCP as the base layer transport or I'll use HTTP. So all optimizations you were at some point trying to do to TCP, now put a layer of HTTP.
Absolutely. So all the theory about this is not kosher for internet routing and it's not unfair to others.
It's all done. All the way down.
Overnight done by Google into the phone. That's what market power does to real world implementations.